can check I mean, 0 is a linear map, yay. And you can check the Frechet quotient. It's just stupid because you get constant minus constant. It's just like this one. It works out to identically 0. Okay, let's try to do one which is not so dumb. By the way, we do not stay in normed linear spaces for the entire semester. The normed linear space stuff has about another 2 hours of life in it, maybe an hour. And then I will exclusively talk about this context for the most part. So it gets much more concrete in here, not too long from now. I have to say things I'm worried about losing. You feel like you're floating? You'll come back down to earth, don't worry. It will get better. It will. It's like I've tried to make the worst possible impression with this class. I mean, the title was selected for me already, and then I do my level best to make the first week the most abstract, difficult week of the course. So yeah, there you go. Example 4. I should get more common sense. Anyway, how about this? If we have f of a equal to a squared, right? The question is, here I'm talking about f being a mapping from Rn by n to Rn by n with the usual Frobenius norm, all right? What's the derivative, is this differentiable map? And if so, what's its differential? Right? So, I'm now going to, where did the differential come from over here? Here we just kind of, properties of limits, we found it. We identified it as something we already knew. Here I just proposed it was the mapping. Here I just proposed it was 0. I haven't derived anything yet. I just guessed, right? This is the first one where we can really kind of derive it. And the way you actually derive it is with the thing I erased. Good job. So what you want to look at is f of a plus h minus f of a, and you just kind of pick off the piece which is linear. Okay? So consider this. This is going to give me a plus h quantity squared minus a squared. What is a plus h quantity squared? Remember, these are matrices. They don't commute, right? Not necessarily. So a plus h squared is a squared plus a times h plus h times a minus a squared. Oh, I missed a very important squared, yes, here. So which part of this is linear in h? Aha! Yes.
Was that the entire purpose of this video?
It may be. I may have changed it back. I had x. I changed it back to a for some reason. Let's hear. So I would propose that we say that df sub a of h is equal to aha. Now, exercise for you guys. You can check that dfa of c1 h1 plus h2 is equal to what? c1 dfa of h1 plus dfa of h2. In other words, you can check that dfa is an element of the linear transformations from Rn by n, well, to Rn by n. So it's an endomorphism of matrices. I'm not going to do that. It would take me 10 seconds, but I'm not going to do it. So what we have to show then is that the Frechet quotient actually is tamed by this thing, right? So let's do that. So we need to look at the f of a plus h, right? Minus f of a minus df a of h, right? And what's that equal to? Let's just look at that expression and come to an understanding of it. Then we'll use that to analyze the Fauché quotient, right? Save ourselves some writing. What is this, though? This is by star. Let me call this whole thing over here star, all right? By star, what is it? Should I write it out again? I mean, so we have a squared, everything cancels, right? Well, let me just get to the interesting part. It's aha minus aha, right? It's aha plus h squared minus aha, right? And there's also a squared canceling, but I'm tired of writing those. The point is, with this being that, everything, what does this actually simplify to? It actually simplifies to h squared, yeah? So we have that the limit as h goes to 0 of the Fauché quotient so we have the limit as h goes to 0 of h squared divided by the norm of h. We need to show that that's 0. Are we on board now? Or, I mean, have I made it confusing? A little bit, sorry. So this limit is probably one you haven't done before, but the norm of h squared, this is a matrix product, right? The product, so this, by the way, is less than or equal to h squared. All right? So we have the following inequality. 0 is less than or equal to the norm of h squared divided by the norm of h, all right? Which is equal to 1 over the norm of h times the norm of h squared, square on the inside of the norm. Properties of the Frobenius norm, that's less than or equal to 1 over norm of h squared. Of course, this is equal to norm of h, right? So as h goes to 0, we find the limit as h goes to 0 of the norm of h squared divided by the norm of h is equal to 0 by the squeeze theorem. But then there's another wonderful thing, which is if the limit as h goes to 0 of blah norm blah equals to 0, that implies that the limit as h goes to 0 of blah is also 0. So if you can show that the limit of the norm of something goes to 0, it implies that the limit of the thing itself is 0. So I've shown that the norm of the Fauché quotient goes to 0, but that implies that the Fauché quotient itself goes to 0. consequently, our aha moment was genuine. So there you go. So apparently, df a of h is equal to aha. There you go. Now, what might you have thought? You might have thought 2a h, right? But doesn't happen because matrix multiplication, not commutative, right? Now, excuse me. Let's see here. So I have another example that's done in this kind of brute force definition style. On page 28, example 2.16, I do a similar thing for a function from R2 to R3. I face the music, I use a squeeze theorem argument to show that my proposed differential works. I find the differential by looking at the difference of, the function at a point plus h comma k. I pick off the linear piece and define to be the differential. I do that again there. So you can look at that. Let's see here. And I'll do some more of these next time. But I think I'm going to shift gears just slightly and talk about the directional derivative. So it's going to take me a little bit of lecture time to actually build up the theory to justify what I'm about to tell you, right? So this is in some sense a look ahead. But what we do is we make a definition that partial f, partial xi is going to be the limit as h goes to 0 of f at the point P, let's say, at P plus h vi minus f of P over h. So we can do this for f, a mapping of norm linear spaces. Interior to the domain of f, okay? So there's a notion of partial differentiation you can talk about, all right? And the cool thing is, theorem, if f is differentiable at P, then guess what? You can build the differential at P now this let me change that h to a t in the interests of not, well, I don't know, I gotta make a choice here. I need a sum over I equals 1 to n of a sub I, v sub I, okay? So here I'm letting v have the span of v1, vn. I'm assuming that the v1 through vn is a basis for the domain. Okay, I just defined partial differentiation with respect to that basis up there. It's just the usual directional derivative idea lifted up to the vector space. We're just looking at the function restricted to a line and differentiating that in the usual way. But if the differential, if ff is differentiable in the sense of Fréchet, then you can build the differential from partial derivatives in the following natural sense. This is equal to Oh man, equal to
Is that P on the end, or is it something else?
P is the fixed point. P is a fixed point where I'm the
Where's the
yeah. Okay, I'm just going to use H. That'll be better. It's just that this H is not the same kind. Fine. So let me just. This is why I was talking about putting a T here to avoid this conversation. Because that has a different meaning. I mean, I'm using H as like a vector in the Frechet limit. So this, though, let me get to the point here. This is the sum, I equals 1 to n, of H sub I partial f partial xi at P, aka partial f partial xi at P is in fact the differential of f at P acting on Vi. This is the relation between partial differentiation and the differential. So we could go back to this aha example, and we could try to build the differential from partial differentiation if we wanted to. And that probably would be an interesting exercise. Let's try to do that. What are the coordinates on our n by n? So example 4, via partial derivatives. So our basis is this one, right? E11, E12, and a few moments later we get to ENN. Right? So if we have ijth coordinate function acting on A, what does it give us? It gives us, it picks off the ijth component. That's the coordinate system on matrices. So to calculate partial f partial xij at P was A here, right? At A, we're supposed to take, oh, you guys don't like limits, do you? I mean, I would rather write this as ddt of f of P plus T Vi, put T equal to 0 at the end. I haven't quite justified taking the derivative of a vector valued function just yet. That's the next couple of examples after the definition. I show that the differential of a vector valued thing could be done component-wise, like the differential of a vector is the vector of the differentials. Okay, so that's better. So we just have to calculate the derivative with respect to time of what? Of f of what? F of A plus T. And then Vi is, the basis is not Vi here, the basis is Eij, yeah. And so what is this? Well, it's A plus T Eij quantity squared, right? Differentiate and then put T equals 0 at the end. Multiply it out, what we got? A squared plus T A Eij plus T Eij plus T squared Eij Eij. So this is this derivative is one we would have. I do these kind of differentiations in my differential equations class. We're differentiating a matrix valued function of a real variable. We just do component-wise differentiation. I mean, you just follow your heart. So that's 0. No t dependence, right? 1. Okay, so what we got is we've got a eij plus eij a plus 2t eij squared. Now we put t equal to 0, so what happens? Right, we lose that 2t piece there at the end. So there's the partial derivative of f in the ijth coordinate direction. It's a matrix. Now we can build the differential from these partial derivatives. df a of h is equal to the sum I comma j equals 1 to n of hij partial f partial xij at a, where hij are the components of h, okay? And so this is a eij plus eija, and see what happens is we got the sum of hij. These are numbers, right? So I can actually pull this a out here by properties of sums. So much writing. Because once wasn't enough. Aha! Okay, there we go. Sorry. I'm just that stupid, but now I know that that's the differential because I already proved today that the differential exists. We'll spend about a half hour of class time proving a theorem which says that if the partial derivatives are continuous at the point, then the differential exists and it can be built in this way. So, but that brings us to the topic of continuous differentiability. And anyway, you probably still kind of feel floaty, don't you? Feel a little floaty? Here, let me bring it back down to earth, and then we'll end class. Well, I'm in class with. Let me end class with a laundry list of what this looks like for usual calculus. We already saw Calc 1, right? Calc 3. Calc 3, we talk about paths, right? Path like r function from the reals to, say, R3, right? So here, the differential of r at a point A of h is going to be just r prime of A times h. Functions. So if I have f from, say, R2 to R, say this in calculus 3, right? Then df a of h comma k is actually going to work out to, well, this again is like the Jacobian of f at this, let me call this, this is a point. I'll keep using a, fine, times hk, but this actually is partial f, partial x at a, partial f, partial y at a. In other words, the Jacobian is the gradient vector for a function from like R2 to R. It's the velocity vector for a path. It's the regular derivative for a function down there. If you look at a coordinate transformation, like we do sometimes, x going from some domain of R2 to R3. We talk about like a patch of a surface, right? Then in this case, the Jacobian of x will be, it will be partial x, partial u, partial x, partial v, where that's actually like xu, yu, zu, xv, yv, zv. Those are the partial velocity vectors we took the cross product of to get the normal in Calc 3. So this might not all entirely make sense yet, but what I'm telling you is this single concept of the differential has within it every derivative pretty much that you've seen in calculus. And a host of, like if you want to ask me how do you differentiate a map from R4 to R6, we have a clear path to do that now. We calculate its change, we find the differential, and we see if the Frechet quotient limits to 0. Well, we have better ways. We use partial derivatives. If they're continuous, we put it together. That's actually calculationally how I like to do it. I try to get away from limits, but okay. Going forward, I'm going to prove all like the natural calculus laws for derivatives on a normal linear space, and we kind of go from there. But yeah.
Is there a geometric notion of this function, like for the differential that we have in the reverse function? We have derivative of f is a slope tangent line.
Right. The truth, so you caught me. I'm cheating a little bit because this whole idea of the differential we're doing right now, we're identifying the vector space we're studying with its tangent space. When we get done with this part of the course, we move to the second part, we'll study that book I made, the required textbook. And when we read the chapter on advanced calculus in there, one of the things we'll learn is that the differential takes tangent vectors to tangent vectors. But there he's making a distinction between tangent vectors in the space. Now that distinction is blurred for us in calculus, right? Because we do this thing with moving vectors from different places and identifying them, right? We don't really work with vectors. We work with equivalence classes of vectors because we say the vector here and the vector here are the same vector even though they're different. We say they're equivalent if they have the same magnitude and direction, not the same base point, right? So that's something I'm cheating on right now in the abstract. And I think to answer the geometric question you're asking, that's partly related. Now, there's some kind of answer I can give you. It's hard to visualize, right? But there is some kind of like, if we set the linearization, what's the linearization? I didn't tell you that yet. And I might have given you a homework problem about that, so I probably shouldn't say a word. The linearization of f at A of h is equal to f of A plus df A of h. So it is, right, it's the best affinization of the function. This is not a linear, it's unfortunate. We call this the linearization of f, but it's technically not a linear transformation because it's got this piece. It's actually an affine function, so we should probably say it's the best affinization. But this is like really close to f of A plus h. I mean, it's the best approximation. It's the best like linear type approximation to that, right? And so if I took this thing and set it equal to a variable, whatever that means, that kind of graph is like the geometric thing which is close to this like curved surface you can imagine being attached to the function, the nonlinear function. I mean, we can recover tangent lines and tangent planes in the sense we already talked about in calculus in more and deeper things if we think, and we'll get back to this eventually. I'll talk about manifolds in Rn, but I'll be honest, I don't really try to visualize it directly. It's not, I don't think it's productive. I mean, but I hope you'll be happy that you have now learned how to differentiate, like starting to anyway, when we get done with this, there's nothing you can't differentiate, like in terms of finite dimensional stuff. Like, it is all under our control. So, anyway, have a good weekend, guys.